Welcome, everyone, to the Ontology Summit 2025. I am Ken Baslowski, and our topic this year is conceptualization, analysis, and formalization. And today is February 5th, 2025. And we have a very interesting topic today about Hilbert's problem that we will be informed about from Michael Gruninger, who, well, maybe will even see a solution to this problem. So I'll turn over the floor to Gary. Go ahead, Gary.
Thank you very much, Ken. Just a few words of welcome to everybody. I'm the organizer of track one, and this is, I consider it the third presentation in that track. And with that, it's a pleasure to welcome back Michael Gruninger, who's a professor of industrial engineering at the University of Toronto and associate chair of undergraduate studies. Michael is familiar to many of us here at the summit and the Ontolog Forum, and like two of our other track one speakers, Nicola and Barry, he was an important part of the first summit, and since then has served in many roles, including organizing later summits, as well as a speaker for many of our summits, such as the Summit on Explanations and Sessions on Common Sense. Like our prior speakers, Michael has played leadership roles in IAOA and as editor-in-chief of the Applied Ontology Journal. According to Google Scholar, his work has been cited by others articles over 18,000 times, and his most cited work is Ontologies, Principles, Methods, and Applications, written with Mike Ushold, and it shows his roots in ontology because it's from 1998. As was true for our previous session, people may use chat for comments and questions, and we expect and hope that there will be some time for proper questions and answers sessions following the talk. As you can tell from all of his past as well as current research and interest in formalizations, Michael is a very apt speaker for this year's topic, and he has as well crafted an intriguing title to his talk that Ken mentioned, The Heirs of Hilbert's Sixth Problem. So everybody please welcome Michael, and the floor is yours, Michael.
Well, thank you very much, Gary and Ken, for inviting me to present to you today. I hope I live up to people's expectations. I was going for a catchy title and ended up generating a lot of interest that way. So let's go back to Paris, 1900. At the International Congress of Mathematicians, David Hilbert posed 23 problems. And these 23 problems had a profound influence on the development of mathematics within the 20th century. Some of these are actually still open. His eighth problem was about the relationship between prime numbers and zeros of the zeta function, commonly known as the Riemann hypothesis. This problem is still unsolved, and within the Clay Mathematics Institute, there's a $1 million prize for anyone who can solve that particular problem. I'm not going to go through all 23. There's just a few I just want to highlight just to kind of illustrate the impact that these problems had. His first problem was on what's called the continuum hypothesis, the question about whether there is a cardinality of sets that's between the cardinality of natural numbers and the cardinality of real numbers. And this question was actually finally solved. Kurt Gödel provided one partial solution to show that this problem is the continuum hypothesis is consistent with the axioms of set theory. But it wasn't until later on in the 60s when Paul Cohen provided a counterexample. So he introduced an entirely new technique called forcing that was able to construct a counterexample in which the continuum hypothesis was false. So there is some kind of cardinality between countable and uncountable. And I just want to kind of raise that point because it actually really shaped set theory after that. The technique of forcing is widely used, and the whole idea of coming up with independence results within set theory, again, has really kind of characterized a lot of the development of set theory in the past 50 years or so. Hilbert's second problem is perhaps even more famous. It was the question of providing a proof of consistency for piano arithmetic. And of course, this was shown to be impossible by Kurt Gödel in his incompleteness theorem for piano arithmetic. So it's interesting. Kurt Gödel actually was involved in the partial or complete solution of two of these kinds of problems. But of course, Gödel's theorem is perhaps one of the most famous theorems within mathematical logic, and that was essentially focusing on the second problem. The 10th problem, maybe not quite as famous as those, but I think it equally has impact on mathematical logic, was the question about whether or not there is a decision problem for Diophantine equations. So Diophantine equation is a polynomial where you're looking for strictly integer solutions. So if these are real numbers, it's decidable. But if you're looking just for natural number solutions or integer solutions, it turns out this problem is undecidable, and that is now called Mathesevic's theorem. And again, this problem is, it's not just the fact that these problems were solved in this particular case too, but it was the techniques that arose out of the approaches to solve this problem that are kind of the lasting legacy of some of this work. So the whole idea of doing undecidability of logical theories, really kind of gelled with Hilbert's 10th problem. But as the title of my talk today kind of illustrates, I'm focusing on a particular problem here. It was Hilbert's 6th problem, and this is a quote from his talk at the Paris conference. The title of it was "A Mathematical Treatment of the Axioms of Physics." So in the investigations and the foundations of geometry, which Hilbert had done some work already in the late 19th century. So this is again 1900 when he's doing this talk. He'd already done some of this work on geometry. So he said the investigations of the foundations of geometry suggest the following problem: to treat in the same manner, by means of axioms, those physical sciences in which mathematics plays an important part. Now, this problem is, I think some historians and mathematicians would say, well, this problem hasn't really been solved to everyone's satisfaction, but that's probably because the problem is not very well posed. It's not the kind of thing to say, well, which physical sciences are you referring to? What actually constitutes a solution to this problem? And in a way, even the statement of the problem is interpreted very differently now than it was at the time when Hilbert posed this problem. So if you think back to 1900, for those of you who are still around, this is not too long after Frege's, proposed his kind of notation, idea of some inference rules in that notation. But this really predates, say the Russell and Whitehead's Principia Mathematica by at least 10 years. So people don't really have a standard notation for first order logic. Gödel didn't come up with his completeness theorem for first order logic for another 30 years. So there's not really any notion of model theory at this point. And even the notion of axioms, if you go back and look at Hilbert's book on the foundations of geometry, where he proposes his axioms for Euclidean geometry that he's alluding to in this statement, they're not written in a formal notation. They are written in natural language, a mathematical, rigorous natural language, but still a natural language. And there is, on some of the statements, I believe there still is some kind of ambiguity when he makes those statements. Again, since then, people have taken those statements and written them out in a logical notation. But at the time, they weren't really in that logical notation. So it's not necessarily clear what Hilbert actually meant exactly by axioms. And I mean, he did have some other lectures. You go back in the history of the philosophy, history and philosophy of math. He did do some lectures in 1905, a series of lectures, and people often refer to these lectures as sort of partial solutions. So further on in the statement, Hilbert will talk about, well, some areas we can look at first would be things like mechanics, thermodynamics, perhaps statistics, probability theory, and people would kind of propose those. And I think even the Wikipedia page I noticed would refer to, there were some axioms for set theory, like Weitmann's axioms for quantum field theory. But again, these were not axioms in the way that I believe, say, the applied ontology community refers to axioms. They really are kind of mathematically formal natural language kinds of statements. But nevertheless, I mean, following Hilbert's original motivation here, I mean, he was referring to the work he did on the foundation of geometry, and those are the kinds of axioms that have ultimately been formalized within a logic, first order logic, and actually, I mean, technically speaking, I think there's some other axioms of that Hilbert proposed that are now be considered to be second order logic. Again, that distinction didn't even exist when Hilbert was proposing these problems. But also what really draw my attention to this issue, and this is, again, these next two slides are extended quotes. That's why I have they were kind of italics. These are extended quotes from kind of another discussion that Hilbert had, that after that particular statement. And it was these statements that really kind of drew my attention to this idea of that was what we do within applied ontology, sort of inspired by the challenge that Hilbert posed in his sixth problem. So first of all, Hilbert says, if geometry is to serve as a model for the treatment of physical axioms, we shall try first by a small number of axioms to include as large a class as possible of physical phenomena, and then by adjoining new axioms to arrive gradually at the more special theories. So again, the idea being that you start off with a small set of axioms that capture, whose models correspond to some set of phenomena that you're trying to represent in some particular physical domain, and then add new axioms to restrict that class of models and get to more and more special theories. I mean, this is, again, very reminiscent of the work that we are doing within applied ontology. One approach is, one way of looking at upper ontologies, or equivalently foundational ontologies, is that there's a very small set of axioms that applies to a wide variety of domains, and that allows interoperability, and then you slowly add some other additional axioms to specialize in different particular domains, whether there's a middle domain or whatever, it's debatable. But this idea of starting off with a very general minimal set of axioms and extending, again, it is part and parcel of what we do within applied ontology. The second point he made, the mathematician will also have to take account not only of those theories coming near to reality, but also, as in geometry, of all logically possible theories. So there's this idea that there's this tension between kind of exploring what are the logically possible theories versus what are the ones that we would potentially need in order to represent a particular domain. And at the time, that might not necessarily be obvious. So if you look at even geometry, people use Euclidean geometry and say, well, that's what we're doing in reality. But of course, Riemann comes along and says, well, we can, and other people, before kind of said, well, there's this parallel postulate. It is actually independent of the axioms, the rest of geometry. So we can come up with some non-Euclidean geometries. And when Riemann kind of created his non-Euclidean geometry that bears his name, there wasn't necessarily a physical application. But of course, we know now that it is the essential heart of general relativity, that general relativity is based on the idea that we're using Riemannian geometry rather than Euclidean geometry. Excuse me. Thirdly here, Hilbert said, the mathematician must be always alert to obtain a complete survey of all conclusions derivable from the system of axioms assumed. So the idea here, and this is maybe a more subtle point, but we actually want to use these axioms for inference. These axioms are not just simply around to say, okay, we have a formal foundation, the world is a nice place. We actually want to use any axiomatization to draw conclusions, either new theorems from the axioms we have, but I think in general, drawing conclusions from that logical set of axioms plus some other data, right? So we're identifying patterns in data and drawing conclusions from the data that we're seeing. And then the final point on this idea here is, further, the mathematician has the duty to test exactly in each instance whether the new axioms are compatible with the previous ones. So this goes to the idea of, his second problem, which was consistency. So we come up with these logical axioms. How do we know that they're actually consistent? And this is, in a lot of cases, we've been talking the past few weeks about ontology quality, but it's been a long-running topic within the Ontolog Forum and Ontology Summit, right, is one of the fundamental requirements for any ontology, before you can even start talking about other aspects of quality, is that that ontology needs to be consistent. And that's what Hilbert's referring to in this last point. And then just one more slide here that, again, of his comments. The physicist, as his theories develop, often finds himself forced by the results of his experiments to make new hypotheses, while he depends with respect to the compatibility of new hypotheses with the old axioms solely upon these experiments or a certain physical intuition. So there's this idea that not only do we want to have a certain verification of our ontologies in terms of logical consistency and the kinds of inferences that we can make from those consistent set of axioms, but there's this idea that also their reality is somehow staring us in the face, and we can't escape reality. We have to conform our theories, our ontologies, to reality in some way. Now, I think one challenge we have in applied ontology, one that maybe physicists have the luxury, physicists and chemists, other scientists really do have a physical reality. I think sometimes when we're doing applied ontology, we're not as constrained, because very often we're building ontologies in the context of information systems, and so there's a little more flexibility in what reality is. But I want to argue today that there is some sense in which we can actually do experiments even in the context of something that's purely of information systems. Okay, so that's sort of a prelude to the 2 points I want to make today. And I want to kind of then, based on what I've just said so far, from these comments that Hilbert made in his speech, I want to ask the question here: are ontologies the axiomatic theories that were acquired by Hilbert as a solution to his sixth problem? And I want to look at this in two different ways. For the first half, I want to talk about this idea that we are providing ontologies for existing physical theories. But for the second half, I want to take the other perspective and ask whether or not we can consider ontologies to be themselves a kind of physical theory, so that we're kind of providing, in a way, new science and new math. So first of all, let's kind of consider this idea of ontologies for physical theories. I mean, what are we really talking about here? And I kind of, based on, again, Hilbert's comments there's actually some other books, some very good books. I think Leo Corey wrote a very interesting book dedicated to this particular problem. And I really find a lot that resonates within, I guess, my methodology, which I guess grandiosely might be called the Toronto School. So these points here on this slide, I kind of follow them myself, but I kind of believe they're sort of inspired by Hilbert. So first of all, what Hilbert did also in his 1905 lectures, he kind of focused first on what are the mathematical theories that underlie these particular physical theories. So, if you look at the way that physics has developed, and we're kind of picking on physics, I guess. I'll have some chemistry examples later on, but just like mathematicians think number theory is the pinnacle of math, I think scientists might think, or physicists think, physics is the pinnacle of science. But if you take a look at how physics has developed, I mean, it's very much driven by the mathematics. Like I mentioned before, when Einstein comes up with his field equations, I mean, they really are talking about characteristics and properties of a Riemannian manifold. So if you look at, again, Hilbert's lectures, when he was saying, well, what if we try to come up with some axioms for mechanics? What he actually started doing was providing axioms for vector spaces, because vector mechanics is very much part of mechanics. And so the idea of what is a vector space, he started turning to those kinds of axiomatizations, like what exactly is a vector space. So he actually started off first with identifying, okay, what are the mathematical theories that underlie this, and then to say, okay, now we identify what these mathematical theories are, let's axiomatize those. Now, that's not the whole story, of course, because the second aspect is, well, what's the relationship between those mathematical theories and the entities and relationships in the physical theories? And so the idea would be, you not only axiomatize the mathematical foundations, but also the relationship between those mathematical foundations and your domain concepts. One way to consider this is the ontology is used for interpreting the equations. So this is something I think sometimes, particularly I think the naive physics work that kind of, it was initiated in the mid 80s. Pat Hayes's paper, kind of the naive physics manifesto sort of idea, right? That maybe we're talking about qualitative things when we're doing ontologies. And so there's this kind of weird mix. Well, how do you combine calculus and other kinds of mathematics with that? And I'm not sure if that's necessarily the way to go. I think the way to kind of think about this is, again, we want the ontologies to interpret what's going on in these equations. So for example, not all solutions of the equations in your particular physical theory are physically realizable. So you're actually, when you're saying, well, this is not, this should not be a possible scenario, you're actually implicitly using some kind of axioms to kind of eliminate that. So for example, if the area of a region is determined by a quadratic equation, the solution with negative lengths is not physically realizable. So that's kind of saying something then about, well, if I have some ontology of space, then negative area is meaningless. Now this can, and I guess another example is even with Einstein's field equations, there are solutions in which time is circular. And so of course everyone says, well, okay, that's physically impossible. But do you add an axiom that says, okay, that's not possible? Or do you have some other theory that extends relativity that says, oh, because of these axioms, because of these consequences, circular time loops are not possible. But this can be a little vague sometimes, because when Dirac posed his eponymous equation, he also came up with some solutions. So he had it's a relativistic wave equation in quantum field theory, and there were some solutions that had negative energy. And so what the heck does this mean? Do these mean anything? And well, it turned out that he had theoretically predicted the existence of antimatter, that was the way to interpret the negative energy solutions to his particular equation. So, there may be, you kind of, again, the whole point here is, well, how do I interpret these solutions? Are they physically realizable, in which case you've discovered some new phenomenon? Or are they not physically realizable, in which case you need to have some additional domain knowledge brought to bear to eliminate those, right? So the idea being here that any axiomatic theory in such a domain, we need to make these assumptions explicit. So one place I think we could start would be units of measure as a way of kind of doing this. And when you're doing units of measure, I mean, a lot of existing ontologies for units of measure kind of focus more on what are the different, classifying the units of measure, and especially doing conversions between different units of measure. But really, if you kind of think about it, I mean, the real purpose to have an ontology for units of measure is because there are physical objects and processes that act upon these objects. And it's a connection between these units of measure and the physical objects that's where we require our ontologies, right? So, for example, how are units of measure manipulated and combined? What is the nature of the entity that's actually being measured? What is the physical interpretation of a unit of measure? So what's the relationship between the unit of measure and the entity that's actually being measured? And this led to some work that we did, I guess this was back in FOIS 2018, FOUNT, which stood for Foundational Ontologies for Units of Measure. And in that work, we actually, for every unit of measure, we proposed having a set of 6 ontologies. Now, some of these were kind of more involved with, so the quantity value ontologies were axiomatizing how units of measure can be combined and how they're related to other units of measure. So for example, if you're thinking of duration, durations can be added together. Durations can be multiplied by a scalar. So, this took half as long, or that took 3 times as long. But you don't multiply durations together. Or, if you do, the product of 2 durations is not itself a duration. So that's kind of what would be axiomatized in the quantity value ontologies. But there were also, again, this idea of, well, what actually is being, what's the purpose of this particular unit of measure? So again, if you're talking about duration, the SI unit is second. So, what's the kind of an underlying generic ontology for duration? Well, it would be, again, theory of time is somewhere. There's an ontology of time underneath there. And not only an ontology of time, but again, some way then of measuring time. So you'd have this idea of, quantity kind ontologies that map, say, a particular time interval or pair of points that implicitly defines a time interval to a particular unit of measure. And then finally, there'd be these physical measure ontologies that again capture that, axiomatize that relationship between the physical object ontologies, right? So now you can talk about the duration of a particular particular time interval. Now the thing though is, again, kind of coming back to the slide that inspired me about Hilbert was, identifying the underlying mathematical theories, and in particular, say the quantity value ontologies in this case here. When you're looking at duration, for example, you can even add durations together, you can multiply them by a scalar, but you can't multiply them. Well, if you look at what axioms kind of capture what I just said, those actually are the axioms for vector spaces. So, by kind of identifying, how are units and measures combined, you identify again what mathematical theories are kind of underlying that, constraining that relationship, and then that provides the basis for when you are actually designing your ontology. That's a kind of a key theme I want to get to towards the end of this talk. So in general, I mean, in that particular paper, we were just focusing on a kind of a smaller subset of the SI units. But I think the idea of a program in this direction would be to kind of look at all the different units of measure and identify the ontological commitments implicit in different units of measure, right? But also looking at the equations that use these units of measure. So for example, velocity, right? Velocity requires ontologies for location, process, and time, right? Because you're talking about an object, how quickly is an object moving? Well, if an object is moving, it's changing its location. So you need to be able to have a location ontology that says, well, at this point in time it's located here, another point in time it's located there. But if there's change involved, well, there has to be some kind of process that's occurring. But velocity also looks at the notion of duration, so that includes time. So even something as simple as velocity, you can see that it's already integrating at least 3 different ontologies. And when you get into more complicated derived units, say newtons, right, which are kilogram meters per second squared, right? Where does that unit, that derived unit come from? Well, it's effectively defined by Newton's law. Force equals mass times acceleration. So by just kind of looking at how newtons are combined, you're implicitly using the equations of Newtonian mechanics. But a fundamental question here, which I cannot answer right now, or today even, I don't even know the answer, which would be, well, what kind of thing is force? I mean, we can represent mass. It has its own ontology for mass and amounts of matter, etc. Acceleration, again, somehow related to velocity, so there's something related to processes there. But what is force? What kind of an entity is force? So you can kind of see how then this approach of providing ontologies for units of measure is using the equations of a physical theory, in this case, as a way of articulating the ontological commitments that are implicit in them. Okay, so that's kind of the first part here, looking at this idea of the ontologies for physical theories. But the second half, what I want to talk about is kind of ontologies as physical theories. Is I think to a great extent, our inheritance is the methodology that Hilbert proposed is one that we use to evaluate ontologies. And so I want to spend the rest of this talk kind of really illustrating and emphasizing that kind of point. So again, just like I kind of see the lasting impact of Hilbert's 23 problems on mathematics, and since he proposed it, it's not so much, I mean, in the specific results themselves, but it's also in all the techniques that were created in order to answer those questions. So I think that's kind of one of this legacy that we have taken up. So first of all, I think I want to kind of just also emphasize when we're talking about ontologies, we are typically talking about ontologies that are designed with respect to a specific set of semantic requirements, right? So we're not just coming up with arbitrary little toy problems or toy axioms to illustrate particular logical languages. We have a particular set of semantic requirements. So one example I use here is kinship relationships. People use this as examples, particularly if you look at the OWL2 or OWL documents. I mean, it is the kind of the running example within the document for illustrating different OWL constructs, because we all have familiarity with kinship relations. Or there's a family history knowledge base, FHKB, which used kinship relationships, but only used as a way of testing owl reasoners, right? But the point, if you had a kinship ontology, you're not just coming up with random examples, you have some set of requirements. So these could be use cases, competency questions that you're actually designing ontology for. So the emphasis here is ontologies are designed artifacts. But of course, I think at least in the methodology that we use here in Toronto, right, the ontology can be considered to be the set of logical theories whose purpose then is to capture the intended interpretations corresponding to a certain conceptualization and to exclude unintended ones. And so we have here, Nicola's, famous kind of diagram here, where we're looking at the relationship between the models of an ontology and the models of its, say, required structures, right, the intended ones we have. And like in general, what happens is, I have a set of axioms, but there are some models of the axioms which I don't want. And these are the kind of unintended models. But there could also be models that have that are omitted. Like I want those to be models, but my axioms are actually too strong, and they omit those as being possible models, right? And so, in general, as you're designing an ontology, at any point in that design process, you'll have this sort of intermediate kind of area here where you're kind of testing, well, are there any unintended models? And as I'm kind of identifying these unintended models, I'm looking for additional axioms that can eliminate them. And if I ever discover that there are some models that are omitted, actually in practice, we find these as I call these unintended proofs, as unintended models. What will often happen is you're able to prove something that you don't want to be provable. I don't have time in today's talk, but there are a lot of these examples where you can actually entail something that's stronger than what you want, and that's again an illustration that there's some model that you're omitting because you want a model that if you don't want something to be provable, you want that model. There's that statement is something that should be able to be falsified. So you can kind of play this game of trying to get your models of your ontology to approximate more closely the intended ones. So this actually has kind of two sides to it. Like on the one hand, we have ontology verification. So that's again the relationship between the intended models of the ontology and the models of the axiomatization. And in particular, we often want to characterize these models. Right? Again, in the Toronto School, we want to characterize the models of the ontology up to isomorphism and then determine whether or not these models are equivalent to the intended ones. Right. And, this kind of plays an important role within semantic integration, decision support. Right. There can, in times, be some models that say, well, I really didn't want those. But, it turns out they're what's called elementary equivalent to your intended ones. There's no first order logic sentence that can distinguish between them, so they don't really harm you. And I admit, there are some classes of intended structures, if you really want them, they're not going to be axiomatizable in first order logic in that particular signature. But I'll kind of maybe we can maybe go through that in the question period. But the flip side of this too is what I call ontology validation. And I think this kind of goes back to Hilbert, that second slide of Hilbert's comments about how the physicist behaves as opposed to how the mathematician behaves. So, the mathematician can say, oh, I've got this mathematical theory and, I understand all of its models, I have a really complete understanding here. But the physicist, the scientist wants to know, well, wait a sec, are these really the right models? Are these the models for me? Right? Are these intended models the ones that I need in order to represent my physical phenomenon? Are they the right ones for me, the user? And as an example of this, I guess this is back to Foyce 2016. We had a paper on the molecular structure ontology. As an example, we have a particular drug here. So this is used in medicinal chemistry. And so you have molecules that have atoms that are joined by bonds. But at a larger kind of scale, there's some structure within the molecule where you're finding there's a field called molecular graph theory where the atoms are vertices, the bonds are edges, but there are these other higher level structures like cycles in a graph, and that's what a chemist calls rings. And there's some paths in this graph, again, a chemist will call chains. So when a chemist is looking at a particular molecule, again, they're looking at that higher level structure of rings and chains and how rings and chains are combined, because that's the effectively the shape of the molecule that plays such a vital role in determining whether or not a particular molecule can be used as a drug to treat particular diseases. So when we were designing MOST, right, we were kind of looking at this idea of, well, how do we evaluate this, right? How do we verify and validate this ontology? So intended models of most correspond to physically realizable molecules. So the validation problem really has these two parts, right? A claim that every molecule is a model of the ontology, and the other direction, every model of the ontology corresponds to a molecule. Now, one way we could actually kind of show, well, in what sense is every molecule a model of the ontology? So there are vast repositories of molecular descriptions. There's a special format. So IUPAC has these libraries. So pretty well any molecule that chemists have discovered has a certain format, data representation format. And we designed some routines that you could take that format, generate first-order logic axioms, and then give it to a theorem prover to determine whether or not it was consistent with most. So, we didn't run through all the molecules, but I mean, in principle, you can take that description of that molecule, translate into first-order axioms, and then determine its consistency. So in that sense, we could claim, at least loosely, that every molecule in that repository, in that database, actually is a model of the ontology that's consistent with the ontology. Kind of going the other way around, I mean, to prove that the models of most are indeed molecules does really require kind of a dialogue with users. So you can imagine having, a model construction, a theorem prover, kind of generating models of most. And again, if each model again is supposed to correspond to a molecule, you would then, well, here's the model, give that to a medicinal chemist, and they could say, well, yeah, this is physically possible. This might be a possible molecule. Let's explore it. Or no, this is not a physically possible molecule, right? In which case you would then try to identify, well, why is it not a physically possible molecule? And that would lead to additional axioms that would, let's say, eliminate that, so it would not be a model. Now, so that was kind of like with respect to chemistry, but this idea of validation, we also kind of recognize that this is actually, like an even bigger problem within ontology design as a whole. And this was some work that we've done in the past few years. This was presented at the Principles of Enterprise Modeling Conference last year in Vienna. We call it the CDO architecture. So CDO as an acronym for Semi-Automatic Design of Ontologies. And the idea was that in the context of enterprises, if you want people to design ontologies, right? One approach is, well, let's design our ontologies first and then try to ground them in our databases and our data sets, our documentation. But another approach is, well, is there some way that we can actually generate these ontologies semi-automatically from the data itself? And so we kind of had three places to start off with. So you could start off with data models, so UML class diagrams, and entity relationship diagrams. And so there's a variety of approaches that can, say, automatically translate those into logical axioms. You could start off with natural language documentation and use semantic parsing to generate some axioms. But what we did was we actually wanted to learn the ontology from the data sets themselves. So the idea here is, like I mentioned before, the idea that a physicist can actually perform experiments, right? So again, there's some notion of a physical world that's independent of the physicist that you perform experiments against, and then based on the results of the experiments, you then, kind of potentially modify your theory. The idea here is that data sets provide that world, right? So that the different data sets are the reality to which our ontologies must conform. So the sense here, the data sets are reflecting the intended semantics. So examples would correspond to clean data sets that have no semantic errors, right? So these should be consistent with the ontology and hence be considered to be intended models of the ontology. Whereas data sets with semantic quality problems should be inconsistent with the ontology. So in a sense, these are counterexamples. And these then would be interpretations that should falsify one or more axioms of the ontology. And so what we did is we kind of constructed this, we call the Hashemi procedure, which is named after my first master's student who kind of first proposed this idea, that given a set of examples or intended models and a set of counterexamples or falsifying interpretations, we want to search through an ontology repository to find the best match, right? An ontology whose models match all the examples and none of the counterexamples. Now, in principle, you may come up with a particular proposal. Now, then you'd want to then go what we call the dialogue phase, where you then kind of generate a set of models and also some falsifying interpretations of this candidate ontology, give that back to the user, and then have the user classify those. So if the user agrees the models are correct, then we conjecture we found the right ontology. If the user disagrees, we refine the search. And if you can't find an exact match, well, then maybe this is the place where the ontology designer steps in, because you kind of know, well, it's the ontology we're looking for is stronger than this one, but it's weaker than that one. So the axioms we're looking for are kind of somewhere in between. We don't have anything in the repository that kind of matches that. So let's have a designer come in. Now, in this particular case, we're using Colore as the repository for ontologies. But one question you might have is, well, wait a sec here. You said this is for designing new ontologies, yet we're looking in a repository of existing ontologies. So how can there ever possibly be a good match here? Because my ontology is new. I don't think anyone's come up with this ontology before. How are you possibly matching with something that doesn't exist, right? So the answer here lies in ontology verification, and this idea that what we want to do is look at the mathematical foundations kind of before we look at the interpretation. So remember, like with ontology verification, we want to characterize the models of the ontology up to isomorphism and determine whether or not they're equivalent to the intended models. So the idea is, when we're doing ontology verification, what we're actually doing is constructing the models of one ontology from models of another ontology by exploiting the relationships between these ontologies. So just as one example, there's a generalization of geometry called incidence structures. So this was the basis for Hilbert's axiom. So Hilbert's axioms of geometry have essentially three modules. There's a module which are like incidence structures, where you have points and lines, and these are disjoint kinds of things, but they are different kinds of things. If you go, you can also, I think he also has like planes. So there's this idea that there's points and lines are disjoint elements, and there's an incidence relationship between points and lines. His axioms also included two other modules, one for betweenness and another one for congruence, which is where the metric aspect of geometry comes in. But we kind of just abstract away that first module of Hilbert's axioms of geometry. We get, in this case here, I'm looking at, again, bipartite incidence, where I have two different sorts of things. And these are, say, 7 different sort of examples, 7 different possible models. So in A, here we have a point by itself, a line by itself. Here I have a point that's in a line. Here I have a point that's effectively the intersection of two lines. In E, here I have a line that is defined by these 2 points. If you kind of think carefully here, this example number F here corresponds to a triangle, because I have 3 different lines that intersect each other at exactly 2 points. So P1, P2, P3 are the 3 vertices of this triangle, and L1, L2, and L3 are the edges of that triangle. So again, this is kind of an abstraction away. And Hilbert proposed a particular set, but again, we remember back to that quote, right? We not only want to consider the axioms of interest in this particular case, we want to consider other logically possible models. And so this is a kind of a snapshot. This is not the entire bipartite incidence hierarchy within Colore, because that's too large. There's almost 100 theories in there, but it gives you a snapshot. So again, the weak bipartite is what's called the root theory, and then that gets extended in different ways, again, following Hilbert's point, by adding additional axioms along the way, right? And the whole idea of that Hashemi procedure I was talking about is that it's essentially doing a search through this partial ordering of theories, again, to find the best match. It's kind of very reminiscent of the version space approach for other oldies out there from the 80s, which was proposed by Mitchell as an early learning technique. Right, but again, the idea here is, when we have this kind of search through this repository. But the other thing to note here, again, is that these are mathematical theories. These are not necessarily theories in your domain. Now, suppose that in that CDO architecture, I was building an ontology for a university, right? So I need to have a course management system in there somewhere. So, I have expressions like professors teach courses. Courses are, taught by a unique professor. Professor can teach at most 3 courses. Students enroll in courses, right? The kinds of things you might find in a nice UML class diagram. So the idea here is, what you're kind of saying is that you're hypothesizing that, I think, because I have these 2 disjoint classes called course and professor, and a binary relationship between them, I think I have, this is related to bipartite incidence. So I have these translation definitions where I make that explicit, that a course, which is again my domain class, is equivalent to point, which is a mathematical object. And it certainly teaches x, y, if and only if x is in y, x is a line, and y is a point, right? So this provides a mapping into there. And so you're taking all of your examples and counterexamples, which is say be from a university database of how people, which courses somebody teaches, which courses someone's enrolled in. And you would find, based on the matching the data, which of these particular bipartite instance theories that is the best match, right? But you're searching through this in the mathematical context. So this is why there could be, in fact, a very new domain ontology for university course management that nobody thought of before, but we discovered it because its underlying mathematical structures had been discovered before, right? And the interesting thing here too is, you can suppose there was not an exact match. Now we kind of combed through a lot of the literature. We have a betweenness theory. We have a betweenness hierarchy in chloride that has 73 different theories of betweenness, and we go all the way back to like 1895. So I think Veblen was the first one to propose axioms for betweenness, and the most recent ones were 2017. So we have over a century of theories that we've gathered from the literature in that particular case. So the idea would be, if you have found a particular domain theory that does not have a match to a mathematical theory within the repository, then you could say, oh, well, your algorithm, your procedure here doesn't work then. You haven't discovered my ontology for me. But there's a sense in which you've actually discovered new math. Right? There's some mathematical theory that you've identified is relevant to your particular domain, but which nobody in the past 100 years or so has ever discussed. So you've identified a whole new mathematical theory, which, again, maybe your client, the university, when they're building their course management system, might not be happy, but I think that's cool. So I want to kind of just end here on kind of a controversial note. And I'm going to call it the chloride hypothesis, that every ontology that we look at within our field is logically synonymous to a combination of mathematical theories that serve as ontology patterns in our repository. So there are some of these hierarchies here are orderings, graphs, magmas, which again are a generalization of groups and rings, groups, semigroups. But there are, so those are kind of widely known, but there are some other ones that are relatively new. Instance structures I kind of mentioned, geometries are kind of widely discussed, but there are other structures that are not as widely discussed. So myriagraphs are the amalgamation of an ordering with a graph. Effectively, that forms the underlying mathematical structures for mirror topology in particular, but also plays a role in looking at things like comparability graphs and other aspects of graph theory. Subposets is when I want to amalgamate two different orderings together. And this actually, if you look at the periods ontology, Van Bentum's book, Logic of Time, he had a periods ontology. And in fact, what you're doing there is you're amalgamating an ordering over intervals like before and after with a mereology of intervals like during. And then there are some other ones here that we've actually constructed as a result of doing ontology verification. So bundles and foliations we ended up creating in order to verify participation in ontologies like Dolce and PSL. Multi-geometries we created as a need to verify ontologies for location, ontologies for constitution. So we did, in fact, I claim we did create some new mathematics in these particular cases. So I mean, that's kind of a provocative challenge I'm putting out there. So just to finish up then, right? I'm actually saying that ontologies are the axiomatic theories that Hilbert asked for as a solution for his sixth problem. I think if we're looking at ontologies for physical theories, we want to focus on that relationship between the mathematical structures and the ontological commitments of the domain. But then finally, I think when I said the heirs of Hilbert's sixth problem, I think we are the heirs, and our inheritance is this methodology of characterizing mathematical theories to be used in the verification and validation of ontologies. So thanks very much for listening.
Well, thank you very much, Michael, for very rich and provocative talk. I know you've covered topics that relate to our two prior speakers, Giancarlo and Nicola. For example, Giancarlo talked about semantic requirements and competency questions. And our next speaker, Barry, I think has a very different view on some of these relationships between mathematics and ontology. So for all those reasons, I'd like to start again, as we have in the past, in the order of our prior speakers and our future speaker, seeing if they have comments and questions now before we go to the more general audience. So starting with Nicola.
Hi. Yeah, thanks, Michael, for this very nice talk. The feeling I have is that Hilbert's dream of axiomatizing physics is really definitely very far from being realized. Especially, I wonder, you insisted on this relationship between the equations and the real world. Finding this relationship is not easy at all. Even for this simple Newton's law, F equals ma. You mentioned that understanding the ontological commitment behind the notion of force is not easy. By the way, there is a brilliant philosopher, Oliver Massen, who has written papers on the metaphysics of forces. So, and for instance, for quantum physics, just the debate is exactly finding an appropriate ontology, because the equations work, they are repeatable, you know, the system, the mathematics works, but still people are debating about the ontology behind quantum physics. So really, this is really far from being achieved. This is just a comment which comes to mind.
Yeah, no, actually, that's a very good point. Yeah, and I did neglect that unintentionally, but I did neglect that particular example, right? So the idea that there can be different interpretations, but have the interesting thing with quantum mechanics, like you said, is that the predictions that it makes are correct, right?
Yes.
It's the interpretations that people differ on, and I'm wondering if that is maybe more analogous to the way that you can kind of come up with, say, different kinds of interpretations of, like, physical interpretations of the same kind of logical theory. So when people are talking about geometry, right, you could say, well, I can think of I know what a line is. But if you're looking at on a sphere, right, then you're looking at great circles. So a circle becomes a line if you're looking on a sphere. And so by interpreting it as a spherical geometry, that kind of differs from what I'm thinking about it as a line on a very long sort of plane. Or maybe another more frivolous example is the Hanoi puzzle, the Hanoi Towers puzzle. So there are these really fun psychology experiments they did back in the 70s and 80s, where instead of moving discs on pegs, like everyone knows the Hanoi Towers puzzle, Towers of Hanoi puzzle, it was monsters holding globes. And you had different rules for a monster could shrink a globe to be small or expand the globe to be large. Underlying the structure was the same. The search space was exactly the same as Towers of Hanoi. But people have a very difficult time understanding it because their interpretation was now based on physical things shrinking and expanding. So it could be the case with quantum mechanics that these are, there's that kind of interpretation that's going on there. So there's not necessarily a functional difference. You can't kind of say, well, here's a counterexample that's consistent with my conceptualization that's not consistent with yours. But no, I think that's another area. I should have addressed that a bit more.
Okay. Giancarlo is currently muted, but might have a comment or question.
Yes, thank you, Gary. Thanks a lot, Mike. This was fascinating. I don't think it's controversial at all, your last point. I like very much this idea of trying to find this kind of homomorphic relation between reality and some mathematical structure, and then this guides the process of finding your axioms, because that's what you're trying to approximate. I like very much the way you put it. So the first comment I would like to make is the connection you make with both our previous talks, right? So even in this analyzing Newton's formula, you're doing an unpacking there, right? So you're saying, what are these things? So what is the ontology behind this mathematical thing? And in terms of what are forces, what is mass, what is acceleration, what are the things that I have to commit to presuppose in order to make sense of this formula? The connection to Nicola is, so your process of verification is about correctness and precision, right? So finding the relation between these two sets of intended and the valid models, the models, but it's also connected to accuracy, right? It actually goes a bit beyond that, because you were saying, you know, the state of affairs in the world, they are telling me what are the things that should be in the set of intended models, but they are actually telling you more than that, which I'm not sure it was captured in your notion of validation, which is the following. Nicola's notion of accuracy, and again, this is connected to this notion of explanation, because when you reveal the ontology behind it, you understand what are the things in the world, right? So what are the state of affairs? And you were saying, maybe the structure of your logical models, right, of your mathematical object, cannot differentiate between two different states of affairs in the world. It was his example with on, right?
Yep.
So it's not only guaranteeing what should be there, but the nature of these mathematical objects, which are your mathematical models. So this is the first thing I would like you to comment on. The second thing is, I like very much this idea of looking at data as your intended models, but don't we have the same problem there of establishing the correctness, precision, and accuracy of your data?
Right.
If you could comment on that as well.
Oh yeah, no,
Thanks.
great questions. Yeah, no, thanks, Carl. Yeah, no, yeah, some great questions. So, I think for the first point, right, the notion of accuracy, right? Again, I think that's something that we really do need to pay a lot of attention to. I think that you're right. I think you and Nicola are right that this sort of has been a little bit neglected. I think there's two ways to look at that. One is in terms of what we call, like, say, definability. So there can be a variety of relations that are definable in a particular ontology. So if I'm using geometry, I can define, you know, collinear as a relationship, right? In terms of these 2 lines are these 2 points are on the same line. But there are other relations that you can't actually define, right? So, in terms of different kinds of connectedness, you can't define strictly in terms of geometry. So that would be kind of, I think, a kind of a mathematical way of looking at this. So if there is some kind of relationship, again, that you are using to say, well, there's a relation that in the restricted signature, you know, these look the same, but I really want them to be different, then you're looking for, well, does that mean that that particular relationship is not definable in my ontology? So that'd be one thing to look at, is kind of looking at this notion of definability, and logicians have some techniques for evaluating that. And so another kind of point that also I think people might neglect too is, there are, when people talk about something's not first order axiomatizable in a particular theory, that really is restricted to that signature. So for example, the concept of evenness is not definable in graph theory, but obviously it is definable in terms of simple arithmetic, right? And so to say that evenness is not first order definable is kind of erroneous. You actually have to say within a particular signature. And there's a lot of other cases where you can actually define something by expanding the signature. And I think that's kind of the point I was going to make, like with this notion of accuracy, is you're right. You would identify, okay, here's a relationship. The existing ontology can't really distinguish between it. So it is, or say it can, in which case I provide definition, or it can't, so it's not definable. And now I hence need to expand my signature to do that definition.
Yeah.
And so what was the second question?
So the second question is, I like this idea of using data as a proxy for intended for things in the world, right? But then you have to deal with these 3 points applied to data now, how precise, correct, and accurate they are. Right.
So again, I think there's 2 points to that. I mean, one would be, like, say, what are the we're kind of focusing strictly on semantic kind of errors in the data, and we're kind of taking the data as given. So I think this notion of accuracy we'd have to say, well, no, I'm taking the data to be accurate, and it's my ontology it's my ontology's accuracy must be evaluated against the data. But I think the data point is a really good one, and I kind of often use the example of COVID data sets to kind of illustrate your point there. That when people were gathering COVID data, it was very ad hoc, and there were a lot of data sets that just are not comparable because they were making different assumptions. If you're in hospital with COVID, does that mean you were admitted with COVID, or you caught COVID after you got there? And some data sets don't make the distinctions, other ones do. Some will use the date where they were diagnosed. Some will use the date that the diagnosis came back. So how long have you been COVID positive? Or since I was tested, or since the result came back? So all these ambiguities in the data. And I think we really have dropped the ball on that from the applied ontology community perspective. I think we need to kind of take a more proactive approach to that, because we could always explain it afterwards. Like, oh yeah, here's the mistake you made using our ontology. But we weren't using ontologies to tell people beforehand, don't make these mistakes, right? And as a result, we almost played like ontology whack-a-mole. So every time a data set came out, we could say, oh, here's a problem with it. But then, okay, you whack that mole, but then another one pops up, and well, you made that mistake. But we could never predict those errors in the data sets. And I think that's where we need to be.
Absolutely. I fully agree. I think this is an essential message. And I think it connects to this distinction between descriptive versus explanatory models, including data models, right? Excellent point. Thanks, Mike.
Yeah, thanks, Giancarlo.
I think getting data scientists to listen to ontologists has been a long-term problem, and I think we've tried. Some of us have tried. Barry Smith's going to be speaking at length on this next week on this topic, but maybe Barry, you could start with a few thoughts and reactions now.
And objections.
Yes, certainly entitled to that.
I thought it was very good, not only because it makes a nice introduction to what I'll be talking about next week, but also because it has a lot of oomph to it. The only issue I would take is with your final assertion to the effect that every ontology is synonymous with a collection of mathematical structures, specifications. I can't remember the exact wording of that statement, but that can't be right. If I have an ontology of rabbit mating behavior, is that going to be synonymous with a collection of statements of a mathematical sort?
Well, okay. Maybe I should provide a few more asterisks and footnotes here. So I was referring, say, to Tarskian semantics of first-order logic. So if we're kind of assuming that, the idea would be that if your ontology is consistent, then you can construct a model for it. And abstractly, that's using, say, set theory. So I have the signature of my model, and for each relation, I have the extension of that relation. So again, I'm kind of using that standard Tarskian idea. So the claim here would be that if you can construct that model, then again, I would argue that it corresponds to one of those theories. So if you have a relation that is metric, then that's going to correspond to a class of graphs. Yeah. If you have a relation that's transitive and antisymmetric, that's going to correspond to a class of orderings.
Yeah, so correspond to is much weaker than is synonymous with.
Well, okay, no. I'll say synonymous with, right? So an interesting example of this. So I mentioned the kinship as an example. So again, back in 2016, we had a kinship ontology paper at FOIS. And at the time we said, well, we have this one particular axiom that says, say, spouses cannot have a common ancestor or whatever. And that was the axiom, but it turns out there wasn't really a mathematical structure that people had kind of looked at there, right? It was well, okay, it's consistent, but what kind of ordering is it? And it ended up turning into a 50-page paper called Locally Linear Orderings, where we actually figured out what that class of orderings was, because nobody looked at it before. And so again, I would argue that if you're consistent, you can construct a model, then it will correspond to some other mathematical theory, just abstractly in that way. And if you have an example, I'd be happy to take up that challenge.
Yeah, no, I agree with the weaker statement that it corresponds to. I just think you miss something if you say it's synonymous with.
But also remember, I'm making a distinction too between verification and validation. So using my kinship example again, right? So mathematically, we had this axiom. So we had this axiom says, spouses cannot have a common ancestor. But you could argue, well, that's not very realistic. I mean, that the English royal family violates that axiom. Queen Elizabeth and her husband were third cousins. So, but that would be kind of a criticism on the validation side. It's like, I can understand what my models are. It's just maybe these aren't the right one for this particular scenario. So I think maybe your point might be.
I don't think we're disagreeing.
No? Okay.
Well,
I
we
will
are
actually
over the
mention
hour.
one other thing. I don't know if you've looked at the European multi-perspective material ontology.
Oh, yeah.
So they claim that because everything in the universe is subject to quantum physics, an ontology which starts out from quantum physics is thereby a top-level ontology which includes all the other ontologies beneath it. I think that's crazy, but it sounds a bit like what you were saying.
Yeah, it's a bit bold. I would agree.
Yeah.
Yeah. I'll have to think about. I'll have to digest that one.
Yeah.
More arguments about what is a foundation, but
Yeah.
we are over the hour and we have lots of comments on the chat. Maybe I have difficulty seeing people raising their hand if they have, but Ravi has many and has been deprived in the past, so maybe we might start there.
Todd has his hand up earlier than me, but if you give me chance, I would ask the question now.
Go ahead, and then Todd, yeah.
Michael, Hilbert space is what is engaging all levels of physicists. Let me recall, starting with people who have worked in relativity ad infinitum, like Chandrasekhar, who referred for his background always the Principia, the Newton's laws, as the starting point. But the point I'm making is that Hilbert space is the basis of almost all fundamental physics today. Whether they talk of Lie algebra, whether they talk of Noether's theorem, and Ken will expand on this in more detail, but let me just convey that multidimensional aspect of Hilbert space is deeply connected to the physical theories of today at fundamental level. Now, the second question is, in geometrical description of Hilbert space, there are always those four fundamental things: dimension, frame, domain, and origin. So that is Euclidean as well as non-Euclidean view of geometry. Where do you draw your power for ontology from these concepts? Even today, people are struggling to understand skyrmions or things beyond standard model using only geometry and topology. So where does ontology stand there?
Okay. Yeah, just before I answer that question, also I posted in the chat here the book by Max Tegmark, Our Mathematical Universe, which also I find resonates with my thinking, and I was talking about today, so people can take a look at that book too. Yeah, so Ravi, I think the key here is maybe not necessarily to think of what we're doing as monolithic. I think one of the benefits and drawbacks of what we do in applied ontology is that very often we're building ontologies for a particular scenario, and so the analogy here would be, well, in some applications my geometry is going to be Euclidean, and some other applications it's going to be non-Euclidean, and it's going to depend on that application. That objection maybe is a little less forceful when we're getting into upper ontologies, because there might be more of an assumption that there should be a single kind of commitment there. But I really do think it kind of, I hate using the word context. I think it really just has to do with, again, ontologies are designed with respect to a set of requirements, and those requirements are shaped by the particular, domain. And so when we are verifying and validating ontologies, we're doing it against those requirements. And so we're kind of relativizing our work in all of those matters.
Very practical approach.
Yeah.
Last point, just before I yield to Todd, is that reverse problem that you said, that every good ontology will have a result with a molecule. Some things are non-real, like imaginary space, so it may not map to every possible thing being a molecule, while
No,
every
exactly.
molecule can have ontology.
No, exactly. No, that was kind of the point, though, right? So that the claim would be that the ontology should do that, right? And the idea would be, like you said, you say, oh no, this particular molecule is not physically realizable, right? I cannot have, these atoms in this configuration because it's unstable, right? So that would be then the missing knowledge in the ontology. So by providing these counterexamples, you would be guiding the design of an extension of that molecular structure ontology. So you'd actually say, well, why is this not a particular, why can't this be a model, right? And that would you then kind of identify, kind of going along Giancarlo's and Nicola's point, right, is that you could say, well, these two models, they, in terms of the molecular structure ontology, these two are kind of equivalent, but for some reason, this one is not physically realizable, but this one is. So if I'm going to add any axioms, I'm going to have to expand my signature because there's something, the distinction between these two requires me to have some new concepts.
I understand. You can use it for validation or verification. Thank you. Very good talk.
If we have time, we have Todd, and then Greg Sharp has a good comment, and Bob and Teagarden has also. So Michael, if you have time, let's try that sequence.
Michael?
Hey.
Am I coming across?
Yep.
Yes.
Okay, quick question. You mentioned the phrase or the notion of semantic error. What did you have in mind by that?
So, like again, we designed the ontologies with respect to a set of requirements. So an error would be, again, either an unintended model or an omitted model. So those would be the two kinds of errors.
But no. You used the phrase semantic error with respect to data, and then you used it again later on.
Oh, so right. So in the real world of data, there can be other kinds of things where it's like formatting came in wrong, or like there's just there's a formatting errors that would kind of come up. Like somebody put an A instead of a 2, or somebody there's like there's duplicate elements in the input file, or it's supposed to be alphabetically sorted, but it's not alphabetically sorted. It's those kinds of errors that are not semantic errors.
Okay.
Yeah.
Those are
so semantic errors have to do with the concepts. Yeah.
Okay. Thanks, Mike.
Greg.
Hey, so I actually saw the question in the chat there, and I'm wondering if your book response actually may be an adequate response. I'll go read that book and see what they have to say. If you have anything else to say, it looks like Janet also put a comment there, so I'll look into those.
Right. Yeah. No. And yeah. Again, I am sensitive to this idea of mistaking the map for the territory. Again, I agree, but again, my favorite phrase here is there's 2 points. So kind of going back to what Barry said, that if you have an ontology that you've axiomatized in first order logic and it's consistent, then there will exist a model. And that model, at just bare bones abstraction, is a set of tuples where each relation, the extension of each relation is a set of tuples. And you're kind of constrained by, if I have a binary relation, there's only so many properties that there can be, and so it's going to fall into like an ordering or a some kind of algebra magma group theory thing, or it's going to be a graph. Like there's not a lot of degrees of freedom there. So if you have those axioms, there is a mathematical structure there. We just have to figure out what it is. I think going the other way around, you're right. I mean, you can run into the danger of maybe being too mathematical and then missing reality because the mathematics is neat and the reality is messy. I think Barry refers to this as stamp collecting. When you create mathematical theories detached from the exercise of applied ontology. But I think that's where the validation side comes in, right? I mean, that's the validation side is telling us, no, look over here. These are the models you want, even if these other ones are more mathematically elegant. And I think one example of this, which I'm actually working on with Gabriele Sacco, who's on the call, and Oliver Coutts, is the example I had from kinship, right? That we had this axiom that says, spouses cannot have a common ancestor. It makes for a very elegant theory, but it's not really true in reality. Well, how can we deal with that? And one way might be looking at things like default logics. And so that would be a kind of a place to say, yes, if I'm sticking to math too much in a classical Tarskian first order semantics, I might be mistaking the map for the territory. And I need to really open my horizons to look at these phenomena that aren't actually handled by framework. But take a look at Max Tegmark's book. I don't have it in front of me right now, but there's a particular page where he has a hierarchy of theories like I was presenting there. So that's what stuck with me.
Is there anything about the other approach? I think that the second side of your talk there, where the emergent properties would become sort of useful within the ontology. So if you have something come from within the ontology and then utilize it for expression, versus there are sort of things that you take as given, like first order logic. What would be the value of developing first order logic within an ontological model, that it sort of becomes self-expressive then, and expressive of things other than first order logic that it could evolve within?
Well, in the context of first order logic, I think one place where this idea of emergent would come up would be to say that that there is an underlying theory that is able to define all the terms in your particular theory. So say using Euclidean geometry, I have this collinear relation I can define, right? 2 points are collinear if they are on the same line. Well, it turns out that collinear is a symmetric relation. If you just look at it abstractly. And so you could say, well, there's this other theory of collinearity that's a kind of a class of graphs, and you could explore that. But the whole idea is, well, that's not really, it didn't really come out of nowhere. That theory of collinearity was defined in terms of geometry. It kind of emerged from geometry. So it could very well be the case that there are ontologies that we have that are, that they are actually definable in terms of some other theory that you might consider to be more foundational. Now, in terms of using first order logic, right? I mean, I talk about first order logic, I guess, in the sense of the first order logic sandwich. I mean, it has enough. The bottom slice of bread means we have to have a sort of minimal expressiveness, and the top layer of bread in my sandwich is the ability to have a sound and complete logic. And so first order logic is the nice meat between those two pieces of bread. If you go beyond first order logic in terms of like towards second order infinitary, you start losing completeness and the ability to have any kind of inference rule. I think an objection of maybe say, why don't I look at modal logic a little bit more? Right, a criticism that modal logic people say, but they also ignore first order. So we have a dispute there. But I agree. I mean, looking at other logics like modal logic, or even looking even beyond, classical logics into things like non-monotonic logics, the role that they play in ontologies is very, very, undeveloped.
Great, thank you.
And lastly, Bobbin, you have a comment? You're muted right now, Bobbin.
Let's see.
There was a stream of from her original posting. Use cases are a specific context of subject matter perspectives, and a number of people sort of responded to that. You might take a look at it in the chat to see if it raised any thought.
Yeah, I agree. I mean, the use case is provides the context for sure. I mean, it's the way if you think of ontology engineering as being analogous to software engineering, right? You typically are providing the set of use cases from which you extract your functional requirements for software. And I would similarly say we have use cases, motivating scenarios from which you extract your semantic requirements. But I think this is a point that Nicola makes a lot, which is, how do you express these use cases in an ontologically neutral way, right? So providing COMPTI questions could be a way of providing these requirements. But if your COMPTI questions have a bias in them towards a particular ontology, then you're sort of, got a circular argument there. So I think that's one potential danger with that sort of approach, right? And I'm very sensitive to that.
So, Michael, this is Mike Bennett. I jumped in on the thread, so maybe I can jump in on this in Robin's absence. So, I always take the point, I stir things up by saying that ontology is the art of not designing something. And you explicitly talked about designing something and equating it to software engineering. And we see a lot of ontologies in the kind of OWL semantic web space, which are explicitly engineered against a particular use case, which works fine if all you're looking at is data. But if you want to know the meaning of things, just extracting what's relevant to a particular use case, particular IT data use case, the data isn't where meaning comes from. You may select data that accurately reflects the presence or absence of particular truth makers, but the data is not the truth maker. And a lot of OWL modelers think it is, because they're designing against one use case after another, rather than saying, what does this thing mean? And then the use case is the context in which you extract the subset of information you actually need to process, but you're not trying to rely on that as determining what the thing means to begin with.
Right. No, it's a good point. I think because I was maybe emphasizing this idea of how we can design ontologies in a semi-automatic way. I think it sort of obscured maybe the application of the ontology, because I think the application of an ontology is precisely to help answer questions that cannot be answered by retrieval alone, right? So if I say Alice teaches math 456, right, then I ask you, who are the instructors in this database? Right, there's no, the only fact I gave you was that Alice teaches math 456. It's the background knowledge that says, well, what is this teaches relation? Oh yeah, it's a relationship between instructors and courses. And so if I know that Alice teaches math 456, I can infer that Alice is an instructor and math 456 is a course. So no, that was not in the data. I had to use this ontology, the meaning of teaches, in order to answer that question. So, you're using ontology together with the data to answer the questions. It's not the data alone. But you could still use that as a way of saying, well, wait a sec, you just said, Alice teaches Bob. That's also consistent. So they can say, oh, wait a second, then maybe I have the wrong ontology or maybe you're using teaches in two different senses there, right? Alice teaches Bob, you really mean that, Bob is enrolled in the course that Alice teaches, so there's that kind of a game that you can play. I was more talking about, kind of trying to learn an ontology from the data as a way of kind of preventing what happens is you sort of design the ontology independently of the data and then try to map it back to the data, and you have to do it all over again. So that's what I was getting at there.
Yeah, I was going to insert a thought like that into it. The idea of the value of use cases and requirements and COMPTI questions, but there's an iterative process in this, as shown by the need to unpack things, as was mentioned by Giancarlo, and you have a way of describing it also, so that you discover things that essentially were hidden in the COMPTI questions to be able to really ask in the process of doing knowledge engineering. You have to sort of do it iteratively and build another, add another small model to it as part of the unpacking.
Yeah.
Well, we've certainly reached the end of our time, and I want to thank you for being very generous with your time, Michael, and thank everybody for being here. And this has been a great introduction also to some of the thoughts that Barry's going to share with us next week. So I hope that everybody will come back and make sure that people know about the talk next week, so we can get a good audience.
Yeah, so I hope this lived up to its the promise.
It's very, very rich.
Thanks, Michael, for revisiting us.
Thanks very much. Thanks for the invitation. Talk to everyone later, I guess.
Okay.
Next week.
Bye, everybody.
Thank you.
Bye.
Thanks, Gary.
Bye, everybody.